Welcome to Summarized Science, where we break down complex research into simple terms. At highway speeds, about 65% of the energy a truck uses is just to fight air resistance, also known as drag. For flat-backed vehicles like vans and trucks, this drag is mainly caused by a messy, low-pressure pocket of air that forms right behind them, essentially sucking them backward. This paper presents an experiment to control that messy wake and reduce drag. To do this, the researchers built a simplified van model and placed it in a wind tunnel. They equipped the rear of the model with 4 sets of small slots that can shoot out pulses of air. The core idea is that by pulsing air at the right time and in the right place, you can change the shape and behavior of the wake to recover pressure and lower the drag. But with so many variables for each jet, like frequency and pulse duration, finding the optimal combination is nearly impossible to do by hand. This is where the smart part of the experiment comes in, a hybrid genetic algorithm. You can think of this AI as a system for rapid, automated evolution. It starts with 100 random jet pulsing strategies, measures the drag for each one in the wind tunnel, and identifies the best performers. It then breeds these top performers, combining their traits and adding small mutations to create a new generation of even better strategies. Crucially, the AI wasn't just told to reduce drag, it was also penalized for using too much energy, ensuring the final solution was actually efficient. After running through 10 generations, the algorithm successfully converged on a solution. It found a control strategy that resulted in a robust aerodynamic drag reduction of approximately 10%. This means the fuel savings from reduced drag would be greater than the energy cost of running the air jets. What's most fascinating is the strategy the AI discovered. It wasn't a simple, uniform pulsing pattern. Instead, the AI learned that the bottom jet should operate at a very low frequency, targeting the large, primary vortices that cause most of the drag. At the same time, the top and side jets were instructed to pulse at a much higher frequency. These faster jets address smaller, more chaotic turbulence in the upper part of the wake. To see what was happening, the team visualized the airflow using a technique called particle image velocimetry. The images confirmed the effect of the AI's strategy. You can see in these diagrams how the jets fundamentally change the flow, lifting the entire wake structure upward and shrinking the recirculation bubble behind the vehicle. This change leads to a significant recovery of pressure on the lower half of the model space, which is the main reason for the overall drag reduction. So, let's recap the key points. Researchers used an AI in a live wind tunnel experiment to find the most efficient way to use pulsed air jets to reduce vehicle drag. The algorithm discovered a complex, non-intuitive strategy that targeted different flow phenomena with different frequencies, achieving a 10% drag reduction with a net energy saving. This work is significant because it proves that a model-free, AI-driven approach can successfully solve very complex real-world engineering problems. In the future, this kind of technology could lead to smarter, more adaptive aerodynamic systems on trucks, saving enormous amounts of fuel and reducing emissions across the global logistics industry. Thanks for watching Summarized Science. We'll see you next time.